Hi everybody, welcome to this Physics World webinar, where we'll be discussing the future of material science with magnetic microscopy. My name is Myla Lloyd and I'm the publisher of Journal of Physics Materials, which is the sponsor for today's webinar. Before we hand over to our chair and our fantastic speakers, I just wanted to take a few moments to introduce you to the journal for those who may not already be familiar. So JPhys Materials is an open access journal highlighting significant and exciting advances in material science. We bring together scientists from across physics, chemistry, material science and engineering with a particular focus on interdisciplinary and multidisciplinary research. Our editor-in-chief is Professor Stefan Brosch, and we have a fantastic editorial board who support us with our rigorous peer review process and research integrity. As a society-owned publisher, any profits that we generate through JPhys Materials go back to the Institute of Physics to help support research, education and science outreach around the world. And we're committed to removing barriers for readers and authors. So as a fully open access journal, authors get maximum visibility for their work. And I'm pleased to share that IOP Publishing has agreements with over 600 institutions now across the world to cover the cost of open access for authors, as well as providing various waivers and discounts. So I encourage you to go and check out the content that we've published in the journal, including the fantastic roadmap that today's talks will allude to. You can visit iopscience.org/jpmatter. If you're still on X, you can also find us there at JPhys Materials, and you're very welcome to reach out to me. So that's Myla Lloyd at ioppublishing.org if you have any questions or want to discuss any potential collaborations. So, unlocking the future of material science with magnetic microscopy. Today's webinar will be chaired by Dr. Dennis Christensen, who's a senior researcher at the Technical University of Denmark. And he's going to introduce each of our speakers, and there will also be an opportunity to ask questions. So to ask questions for our speakers, please use the ask a question function in the little pop-up that you'll see on the side of the webinar, and then Dennis will put the questions to the speakers at the end of each talk. That is all from me. I'm now going to hand over to Dennis to give a bit more of an introduction.
Yes, thank you, Myla. So we're conducting this webinar following the publication of the roadmap on magnetic microscopy techniques and their applications in material science that was published earlier this year here. So in this scientific roadmap, we have been inviting experts in various magnetic microscopy techniques to share their view on the current capabilities of the techniques, what we can expect in the future from these techniques here, and how that would impact material science. Next slide, please. So this roadmap, this is encompassing a lot of different magnetic microscopy techniques, including also scanning probe-based techniques such as scanning superconducting quantum interference devices, nitrogen vacancy magnetometry, magnetic force microscopy. But it's also encompassing detecting magnetic fields and magnetic states with nuclear magnetic resonance and techniques based on optical light, X-rays, and electron-based techniques. Next slide again here. So today we have selected 4 of these topics here that will be presented in this webinar. So first, Katja Novak will be presenting on scanning superconducting quantum interference devices, so scanning SQUID. Next, Christian Degen will be presenting nanoscaling nuclear magnetic resonance. Next, Claire Donnelly will be presenting coherent X-ray magnetic imaging. And lastly, Matthias Chloe will be presenting scanning electron microscopy with polarization analysis. So with this, I would also ask you, Katja, to start sharing the screen here, and then I'm going to introduce you also here.
Right, unmute.
Perfect, yeah.
Yeah, okay, cool. Well,
so maybe I introduce you first here.
Okay.
So Katja Novak You received your PhD in physics at Delft University of Technology back in 2009. You then did a postdoc at Stanford University on low temperature magnetic imaging using scanning squid. And in 2015, you joined Department of Physics at Cornell University, where her lab is now developing magnetic imaging techniques to study quantum materials and devices. With this, I would like to leave the word to you, Kathy.
Okay, cool. So thanks so much for the introduction, and I guess I'll go in presentation mode now. And I have to myself a little bit. I think I'm good. All right, yeah, so thank you so much for the introduction, and I'm excited to be part of this webinar. I will be focusing no, the title is still pretty general, so that's the topic of the webinar, of course, local magnetic measurements for studying quantum materials, and I will be specifically focusing on scanning squid microscopy, and I contributed a chapter to this roadmap together with my colleagues Davidas and Bina Kaliski at Bar-Ilan University. Okay, so let's see. Here we go. So local magnetic measurements provide a unique window into looking at materials and devices, and that's by virtue of a very simple argument, and this is still very general. Magnetic moments and moving charges produce stray magnetic fields, and these are at the heart of many of the phenomena that interest us in materials and devices. And so if you can probe this stray magnetic field, of course, you're going to learn something interesting about the phenomena that interest us. I will focus in this presentation on magnetic probes that measure really that stray magnetic field above the surface of a sample or a material. And you know, roughly, if you have that capability, you can there's several different measurements modes that you can execute or look at. And if I have to divide them, as we did in the roadmap, I would divide these in, say, doing magnetometry, where you really kind of just pick up the stray magnetic field, say from an isolated magnetic moment or a magnetic landscape. You can also locally perform magnetic response or susceptometry measurements, where you need an additional local way of applying a local field, and then you can detect the magnetic response. And this is a version of magnetometry, but is worth kind of highlighting separately. If you can measure the stray magnetic field above a sample, you can measure carefully the Ørsted field generated by a current flowing in your image, in your material, and by that you can actually image how currents flow in a sample. Okay, so I thought like the best way to showcase scanning squid microscopy is to jump in and give you quite a few of examples of measurements that have been done. This is not at all a complete list, but I just want to give you a flavor of what scanning squid can actually do. And so first off, you of course measure magnetic properties and responses in a sample or material. And so one example of this would be work from Bina Kaliski's group, where they've used it to study vortices in this exotic superconductor 4Hb tantalum disulfide, and uncovered a curious magnetic memory effect. You can measure magnetic response, and in the case of a superconductor, that's the local diamagnetic response. And my lab has used that to study a strain modulated superconducting transition in these focused ion beam defined microstructures. A strength of a probe that measures the strain magnetic field above a sample surface is that you can probe functional and process devices. It's not inherently a surface sensitive technique. And so here are two examples where this was done in the, actually that was my postdoc work in the lab of Catherine Moeller. We imaged how the current flows in this murky telluride hall bar, And this was a whole bar process, just the same way you would process it for a transport measurement. It even had a top gate on top. And here's another example of a device pattern and tungsten ditelluride, where the group of Ali Zeldov kind of detected kind of this vorticity associated with hydrodynamic or viscous electron flow in this material. You can use, if you can measure stray magnetic field, you can visualize electronic transport and magnetic textures. So, for example, Bina Kaliski, during her postdoc in Catherine Moller's lab, imaged how current actually flows at an unpatterned LAO-STO interface. And she found these curious modulations in the current density that you see here as stripes, and traced those back as being related to the structural domains developing in strontium titanate. Here's an example from the group of Hans Hilgenkamp, where they have measured emerging ferromagnetism at a different oxide interface, LMNO STO interface. And they study this as a function of thickness of the LMNO. So that shows that you can really kind of uncover magnetic textures using a local magnetic probe. So when you do have a local probe that can measure the stray magnetic field, you don't only have to think about imaging, but it can also be amazingly useful to have very high sensitivity to samples with small sample volumes. So here's an example where in the group of Andrea Young, they've detected the orbital magnetization associated with an churn insulating state in twisted bilayer graphene. And here's an amazing example from Ali Zeldov's group, where they've actually measured the Haas-von Alphen oscillations that you might measure, for example, in a bulk sample with a torque magnetometry in a tri-layer graphene samples. And so you need a local probe to do these measurements, just because these van der Waals samples are atomically thin and only a few micrometers across. And so any bulk measurement of, for instance, the Haas-von Alphen oscillations will not be possible due to the thickness strength. Okay. Some more considerations on local magnetic probes, even within scanning squid microscopy, and we'll get there in a moment. Quite a few flavors and different types exist. And so that led me to think about what are relevant probe characteristics that you should consider. And what comes to mind, of course, immediately is always spatial resolution, but you could also think about what's the magnetic sensitivity of my sensor in terms of magnetic field, in terms of magnetic flux, and maybe I'm interested in measuring currents. It's not listed here, currents or the magnetic moment or spin. But there's also other characteristics beyond spatial resolution and sensitivity. You might also worry about the bandwidth of your sensor, how invasive is it to the sample that I'm trying to probe, how interpretable is the signal that you're measuring. So for instance, does my sensor have a linear response to field or a nonlinear response? How easy is it to use? That includes like how easy is it to destroy your sensor? What's the temperature range it operates in? What's the magnetic field range that it can operate in? And there's probably other characteristics you might care about. And when you look at scanning probes that measure stray magnetic fields, so there's a lot of other, of course, local magnetic sensors, some of which we'll hear about in the coming talks. But if I even just list the ones that measure stray magnetic field, there are the squids that I'll discuss a little bit more. But there's also Hall probes, there's nitrogen vacancy centers in diamond that have different measurement modes, but one of them would also be to just detect the stray magnetic field above a sample. And so and then finally also giant magnetoresistance sensors, which are mainly employed at room temperature. And so there's this whole wealth of different local magnetic probes. And if you ask me, okay, which one is the best here, the answer I will give you is which magnetic probe here is the best depends really on what you want to measure. All right. So now zooming in on squids. So squids are flux sensors. So a squid is a superconducting loop interrupted by two Josephson junctions. And if I do an electrical measurement on the squid, if I flow a current across the squid and I probe the voltage that drops over it, then I get a plot like this, where here it's the current that I flow across the squid. Here is the labeling is a little bit off, but that's the bias current I apply. In color, you see the voltage that I measure across the squid. And then the vertical axis here is I'm actually modulating the magnetic flux inside the squid loop. And you see that there's a lot of features and structures. You see the range where the squid is really superconducting, so you can read off the critical current of the squid. And you see this periodicity, which is given by the flux quantum, which is about 2 millitesla times micrometer squared. In experimental units, shall we say. These squids are typically, we do not just, for instance, detect the critical current of the squid as we change magnetic field. No, these squids are actually typically embedded in a pretty complicated readout circuit that involves an inductive coupling to a squid array amplifier and a shunt resistor across the squid that effectively allows you to voltage bias the squid. And then the signal that we measure is the signal from the squid array amplifier, and it tells us at a fixed bias across the squid, how much does the amount of current flowing in my squid modulate with magnetic flux in the squid. All right, and if you have to way to, in addition, couple flux into the squid, in addition to what you're picking up with your local loop, you can realize a flux locked loop that does allow you to linearize the signal. Okay, so how does scanning squid, so let me give you one example of how a scanning squid might look like, and that's what kind of the community is drifting towards calling a squid on chip. So that refers to the fact that the squid here is really fabricated on a chip. This squid is actually really large. This is a millimeter scale bar. And the Josephson junctions in the squid sit somewhere in the center of the circuit, and has a number of bond pads to connect to the IV, to additional coils that are present in the squid. If I zoom in, that's the kind of like sensitive area here, or the area that does the sensing. If you're lucky, you have a deep edge around kind of the sensitive area right here. You see the pickup loop of the squid that does the actual sensing. There's a superconducting shield shielding the leads of this pickup loop. And then there's the field coil that enables local magnetic response measurements. If you're unlucky and you don't have the deep edge, you actually have to go and hand polish this chip to a corner. And that's an example shown here. But the features are the same. There's the squid loop and the field coil and this niobium shield. And then, of course, you take this chip, you align it under a fairly shallow angle towards the sample, bring it close, have it on a set of scanning stages, scan it around to create an image of the stray magnetic field coming out of your sample. What does the squid see? So the squid is inherently or intrinsically sensitive to magnetic flux. So if I think about the noise in my squid, I'm going to show you a spectrum of the flux noise of the squid. And it's quite generally true that squids have 1/f noise, so the noise as the frequency goes lower actually does increase. And so what does that mean? So we want to measure stray magnetic fields. So how do I think about this? So the flux that I measure, I can think about as being the convolution of the Z component of the magnetic field convoluted with what I call the point spread function of my squid. And this point spread function we can actually very carefully characterize if you image sources, known sources of magnetic field. And so for us, often those are abricosal vortices in a thick superconducting film. And so we can image these vortices and then reconstruct the point spread function that goes into this convolution. And then if you ask how sensitive is the squid to different sources of magnetic field, really depends on the geometry of the magnetic field source. So are we talking about isolated magnetic moments? Are we imaging currents? Or are we actually interested in in measuring fairly uniform magnetic fields. And the geometry of the source of the magnetic field also determines how your sensitivity scales as you shrink or increase the size of your sensor. So for instance, the sensitivity to a magnetic moment actually does increase if you decrease the size of your sensor, because a magnetic moment has these field lines that close on themselves. Whereas if you're interested in sensing rather uniform magnetic fields, you actually gain by making your sensor size bigger, because a smaller field translates into the same amount of magnetic flux. Your sensitivity also changes with frequency due to the frequency-dependent flux noise in your squid. There are quite a few different types of scanning squid sensors at this point. So I introduced you just now to the squid on chip, but there's also pioneered by Ali Zeller's lab at Weizmann. There's the squid on chip, where they essentially do multiple evaporation steps and fabricate a squid onto a quartz tip, a hollow quartz tip. They evaporate one lead on one side, another lead on the other side, and kind of a little ring on the apex. And you get in between the two leads, you get kind of granular constriction Josephson junctions. And so here are some SEM images, and this works beautifully as a squid with a very high spatial resolution. I missed to mention that the squid on chip has a typical spatial resolution of maybe 1, more realistically 2 micrometer. Here you can go down to a few hundred nanometers. And then there's also more recently the group of Martino Poggio developed squid on cantilever, where they fabricate a squid using a focused ion beam on the tip of a commercial AFM tip. Okay, so there's some differences. The differences are in spatial resolution. This squid sensor specifically is very good in co-recording high quality topography. There is differences on if you can have on-chip circuitry or not, which might enable local magnetic response measurements, or having a flux-locked loop. There are differences in terms of these two sensors. You really fabricate one by one, whereas squid on chip you actually can fabricate in like more on a wafer scale. You could compare how robust the sensors are, what their noise performance is, and what I find actually quite interesting. What I don't like mainly about the squid on chip is that it actually does not work in a high background field, whereas these flavor of squids can actually also image in a finite field. Okay, that brings me, and of course it's desirable to combine all advantages in one approach, and that is the perfect bridge to thinking just for 1 or 2 minutes about what could squids do in the future. And so one hope that I have is that we can actually take these different approaches to scanning squid microscopy and combine the advantages that you see there in one platform. Of course, it's never going to work perfectly, but one idea that we have is why can't we develop nano squids but on a chip? And here I show you a possible design. The deep edge structure is actually from a scanning single electron transistor from Shahar Ilani's lab, and this is a picture from this paper here of one possible planar geometry of a nanosquid. And so this is something that you can make with e-beam lithography and RIE etching in the clean room. And so what could be targeted capabilities of getting the high spatial resolution and being able to image in an external field. But if you develop this kind of platform, you can bring back local magnetic response measurements. Maybe you want to linearize the signal, maybe you want high bandwidth, maybe you want wafer scale fabrication. And so what that comes with a set of requirements and opportunities. For the high spatial resolution, you need a small squid loop that you can scan close to the surface. That will most certainly require these weakening junctions. But if it is all fabricated by E-beam, you can add field coils, you can add shunt resistors and capacitors. So you have this capability of adding additional on-chip circuitries. And maybe most importantly, you can share sensors with the community. One aspect I'm really excited about is that Josephson junctions are really inherently fast devices. And so there's directions with squids and Josephson junction devices at large to get to much higher bandwidth and temporal resolution. And one direction that is actually already under development is to realize a microwave readout for a squid. That requires to have, if you have your squid here, that requires shunting it on chip with a capacitor. Then these two will form an LC resonator, where the L is the squid and depends on the flux in the squid loop. And so then you can apply a microwave or dispersive readout to read out your resonator, and that's actually done here. And you can retrieve the flux that's threading the loop. So the LC resonance of that resonator does modulate with the flux that you apply through your squid. And that can, in principle, improve sensitivity and also give you much higher bandwidth for scanning squid microscopy than we have today. There's one way to get even higher time resolution, and there's actually the circuit that has been realized now already quite a while ago, which is a sampling circuit. So this is not kind of an open loop measurement bandwidth, but they have demonstrated a sampling circuit with 40 picosecond time resolution. And this would be useful to, for instance, measure magnetic signals and pump probe experiments. One direction I'm pretty excited about, which is still a little vague in my mind, though I think this is a valid idea and has been pursued previously too. There is a possibility to use Josephson junctions as spectrometers and at the same time also as sources of high frequency signals. And that's nothing new, but an interesting, intriguing question is, can we actually build a scanning Josephson junction spectrometer? All right. Just like probably 1 minute run through of some research from my lab. A lot of the work we've been doing kind of, oh, now I see a bubble. So I'm running out of time. Okay, so a lot of the research that we've been doing focuses on actually understanding local electronics transport on the local scale, and I'll spare the motivation. And maybe I'll, if I'm truly out of time, I'll actually keep it at this, at the two vignettes. One is that we've used local magnetic response measurements to understand a very unusual looking superconducting transition in a focused ion beam defined structure made from cerium, iridium, and indium-5. And what our work allowed us to do is to actually uncover that there is inherently built-in strain in these microstructures. And then in the case of cerium, iridium, and indium-5, that gave rise to really amazing kind of like spatial modulations of the superconductivity in a way that we could even simulate in COMSOL. And so then you could even use this as a strategy to engineer really interesting strain landscapes. In more recent work, we've been asking the question, how does the current actually flow through a so-called quantum anomalous Hall insulator? The consensus in the literature is very strongly the current should flow through the edges in these samples. But in our data, we very clearly see that in the dissipationless regime, while simultaneously measuring transport, we actually find that the current flows in the bulk, in the interior or the bulk of the channel in this quantum anomalous Hall sample. I'll leave it at that and maybe open up for questions.
Thank you very much, Katja. And for the audience, remember to put in questions in the chat here. So we have one question here.
I'll very quickly go to my,
yeah.
you can look at my acknowledgements while I answer questions.
Yes. A limitation of the scanning squid is the low operating temperature. How are the prospects of raising the operating temperature with either a high TC superconductor or large temperature difference between the sample and the tip?
So those are two valid ways, and so my understanding is it's still not simple to make reliable Josephson junction in high TC superconductors that are also kind of really on this small, essentially. And I think you can do it. The question is what kind of noise performance you might get. So I'm not very knowledgeable in that direction, but I would like the question that I would ask is, yes, you can make squids out of high TC superconductors, but is it worth the effort given the noise performance that you get? Because if you want to do higher temperature measurements, you might also go and use scanning Hall probe microscopy. Nitrogen vacancy centers in diamond work from room temperature down to low temperature. Of course, and you have to kind of have an optical setup that would be a requirement for that. But certainly, if you're interested to do higher temperature magnetic imaging, squids are not by far not your only choice. And same holds for people have made a squid inside a cryostat, and I think you need at least 10 micrometer standoff between kind of the cold squid and then some kind of a very thin window-like structure, and then coming out to room temperature. I think people have maybe 10 micrometers is even real optimistic. I'm not quite sure what the distance is, but it's tens, maybe even 100 micrometer or whatnot, at least. Yeah. So if you want higher temperature magnetic imaging, I would almost say like look at a different magnetic probe.
Yes. Another question here also. You mentioned that one of the downsides with the planar squids are the lack of measurement capability in high background fields. Do you have examples of where that could be interesting?
So for example, I have, if I had talked more about my own research, it would be very clearly motivated. But yeah, so the kind of squid on chip that I use work maybe up to 10 millitesla applied field. And then it's just the Josephson junctions. They have niobium insulator, niobium junctions. The critical current just dies off, and I think it is actually related to something like the Fraunhofer pattern in those junctions. Well, I told you that we've been imaging quantum anomalous Hall samples. The reason we actually image those is that those have a quantized Hall effect in zero magnetic field once you magnetize your sample. So no problem, we can image this. I would love to, first of all, image these samples as they go through the magnetic reversal, which requires some hundreds of millitesla field. But more importantly, I really would love to do imaging of currents in very high quality quantum Hall samples. But the quantum Hall effect requires the application of a high magnetic field. And so that would be one idea. If you, and like one physical phenomena to be imaged in magnetic field. But there's many other things as well. Like there's maybe re-entrant superconductivity in some compounds that happens at higher fields. There's studying magnetic materials under magnetic field as you magnetize them and whatnot. And yeah.
Thank you very much, Katja, for your presentation here. I think in the interest of time, let's move on to the next speaker. So Christian Degan, if I can have you to share the screen here. We'll introduce you in the meanwhile here. So Christian Degan joined ETH Zurich in 2011 after positions at MIT, Leiden University, and IBM Research. Christian's background includes a PhD in magnetic resonance and postdoc in scanning force microscopy. Since 2009, he has led a research group on quantum sensing and nanomagnetics. And he's also the co-founder of the microscopy startup QSaber. Thank you very much. Take it away here.
Great. Thank you, Dennis, and wonderful to have you all here. I will try and take the next 20 minutes to show you some of our ideas on nanoscale magnetic resonance imaging. And the article you can read up has been prepared by myself and also Alexander Eichler, who's co-leading our group. Before I start, I would like to say that nanoscale MRI is not a technique, it's a field. So it's an idea, and this is what the cartoon refers to, is whether it would be possible at all to bring MRI down to the nanometer or even atomic scale. The original proposal in the 90s by John Seidels was to have a technique that could image biomolecules and even record their atomic structure. So the idea becomes, the push comes from biology. So it's also a material, but maybe not the material you would be expecting to hear a roadmap on material science. So let me introduce what the ideas or the concept between nanoscale and MRI are, and the most familiar one that you all know is magnetic resonance imaging as such. And if I have to highlight two things about this technique, it would be that it's three-dimensional, something obvious if you're in an MRI machine, but also that it uses low energy radiation. And this is very important if you want to do, let's say, clinical medicine, but also if you do want to study biological matter at the nanometer scale. The expense of this is that the technique is very insensitive. So if you have low energy, the quanta involved are very small. And also to reach three-dimensional resolution, you can't rely on diffraction like wavelength effects. You're always in the extremely long wavelength, so the near field regime. So in order to push this to a small scale, you need some second technique, which is offered by local probes. This could be an AFM or a scanning probe. There are also other approaches, but let's for the moment now say it's a local probe that brings in the nanoscale resolution and hopefully also a way to detect signals, to overcome this sensitivity barrier to detect these very weak nuclear magnetic signals. There is space in the middle. This is the third ingredient, which I think is also very important, in that if you can do NMR at those scales, you get a lot of spectroscopic information. You can, for example, do an atomistic characterization. So if you would look at these colored dots on this biomolecule, you could pinpoint which types of elements or nuclei are sitting at which positions. Once you realize this potential, you also have a tool to control the quantum interactions ultimately at the single spin level, which can then bring you to another field of quantum science, which may not be related to the biology idea anymore. So there's a lot of potential things you can try and do if you can cover these three aspects in one technique. So now moving along from here, a lot we do, I would say 95+% is working on technique, on making this better, and this is what brings us also to this community. So if you look at the really big challenges to do nano MRI, I would say there are two. There is one, and then a second two, and then many others. But the really big one is sensitivity and SNR. So how can you somehow detect a very small number of nuclear spins? And just to give some numbers, if we take a conventional MRI machine, the sensitivity is roughly limited to 10 to the 18 nuclear spins. You can push this down to 10 to the 12 if you make really microscale circuits, but this is roughly very dense. And translated to imaging, this will be a size of tens, hundreds of micrometers, so barely nano. If you compare what we would like to have for an atomic technique, it's one or some bunches of spins, 10 to the 3, 10 to the 4, which would correspond to voxel size in the nanometer range. So this is one big thing that we have to overcome, is how do we bring the SNR to a level where you can detect few spins. The distant second is the magnetic gradient. So if you look at the imaging resolution in the MRI machine, it's limited by detection sensitivity, but it's also limited by the gradients that we can generate with these large coils. And also to give some numbers, the gradients you achieve in really high-end MRI machines are on the order of 10 Tesla per meters. But if you think of the gradients needed to distinguish spectrally nuclear spins very close to each other, nearly on the order of 10 to the 6 Tesla per meter. So we need a way to generate very strong gradients at very small scales. And oftentimes techniques that we use, they bring it together, or we have to separately address the two aspects of sensitivity and magnetic gradient. In this roadmap, we put forward 3 techniques. There are actually more. So SQUID is not on the list I'm going to show, but they may also be one of the tools, and there are a few others. that have seen most efforts in trying to implement this nano MRI. And one way to categorize them is to look at the imaging range, so the size of samples they might image, and also at the resolution you can expect from them. And probably not surprisingly, if you have a big object, if you try imaging it, you're probably not going to reach atomic resolution. Whereas if you have a technique that achieves atomic resolution, it may be quite hard to image, to have this resolution available on a large scale. So the imaging range and the resolution are intimately tied to each other. And you could say there is a factor of range to resolution, which could be 1,000 for MRI, which is a very good number, but only 10 maybe for a technique which is very local. The technique that has seen most work, and we've also been pursuing in our lab, is nanomechanical detection. So you would have a mechanical sensor, and the signal is given by a force between a small magnet and a spin sample. There is a microstrip shown, which is used to do magnetic resonance on the spins. But then both the magnet generated gradient and the force produced is picked up by the same mechanical sensor, for example, an AFM cantilever. Another technique that has come along 10-15 years ago is spin centers, so optical methods to detect spins, most prominently the MV center in diamond, but there may be other ways, where you can read out specific electron spins and then use them to probe the couplings to nearby nuclear spins, and with this you realize some sort of NMR detector. On the very low end is scanning tunneling microscopy. So originally used to probe magnetic atoms, the field of ESR STM has been expanded to also detect very narrow resonance electron spin, or sometimes even nuclear magnetic resonance signals from single atoms on surfaces. So this would be the extreme scale of atomic, but this may be hard to scale up to a large range. And I'll spend some time on the three of them, mostly on mechanical detection, also to introduce the challenges and approaches, and then proceed to the others. If you look at mechanical sensors, it pays off to just look at what's around in terms of mechanical sensors, and especially extremely sensitive mechanical sensors. And if you spend some time, you find an extreme variety of mechanical sensors, and despite AFM being quite a decade-old technique, there are still new sensors coming along every year, nowadays mainly through optomechanics. So most familiar are the ones in the middle, which are these cantilevers, which can make extremely thin and then they become very force sensitive. On the left, you see even larger sensors, but they are competing with the ones in the middle, which are membrane, two-dimensional membrane type sensors that you can structure to have extremely high quality factors and then allow you to have quite a large device to, that still achieves a very good force or spin sensitivity. On the other hand, there are bottom-up methods where you can grow sensors bottom-up, most prominently semiconductor nanowires, but you could also build them by carbon nanotubes or sometimes even grow them in a FIB, like in the Podger group. The other ingredient, so this was the sensor in terms of mechanics, are gradient sources, and those can extend beyond mechanical sensors. So you can ask yourself, how can I produce very localized high gradient magnetic field at the nanoscale? And if you have high fields at the nanoscale, it immediately means you have a high gradient. And to have controllability, you want to be able to not just put the magnet there, but maybe also have a way to change the axis of magnetic field or change the axis of the gradient. So thinking of MRI in clinics, there are 3 gradient coils which allow you to apply gradients in all 3 spatial directions, and only this can then give you a 3D image of your body. So starting at the low end, people have built electromagnets. Here's an example from the Reinhardt group, where you can pass different paths of currents to produce 3D gradients at the center of this device. They're ordered roughly by the gradient they achieve. I'm not quoting a number, but you get an idea from the lower scale on how large the gradients are. One of the early attempts in MRFM, so the mechanical detection of magnetic resonance, was to use magnetic tips on cantilevers, which is feasible, but it's challenging because you combine 2 sensitive elements in one device. So a very hard to make magnetic tip on a difficult to make cantilever. More recently, the Budaktin group has introduced nanoscale constrictions, for example, of silver, where they can pass extremely high currents and produce with an electromagnet fields that are competing with these magnets from magnetic materials, which is amazing because you would think the magnetic materials produce the highest gradients at this scale. A gradient that we've used since my postdoc, which was brought forward by Martino Poggio, was to use evaporated nanoscale tips on strip lines to do mechanical detection of magnetic resonance. We've worked on this design and realized some of those tips that are now embedded in strip lines to have a very planar surface, which is more suited for imaging because there is less interactions with the topography. And if you look at the very far end, what are the highest gradients people have made? I will claim, at least at the 10 nanometer scale, these are the magnetic write heads from hard drives, where you need a very localized high magnetic field to write bits, and they achieve on the order of 30 million Tesla per meter. But then they're made in a fab that you cannot have in your own local laboratory. So let me give you some milestones and prospects of mechanical nano MRI. One of the most famous experiments shown on the left is the single spin experiment by Dan Ruger in 2004 at IBM, where they were able to detect single electron spins. We've later extended this to try and measure NMR signals. For example, the virus imaging experiments at the bottom, where you can see individual virus particles in an MRI scan on a roughly 10 nanometer length scale. And in my opinion, one of the most advanced setups are these nanowire sensors with constrictions pursued by the Budakian group, where they can reach sub-nanometer resolution and start imaging on the scale of atomic lattices. These devices can be used for other things, although we mostly pursue them for nuclear spin detection. I just want to measure non-contact friction as a recurring theme also in other areas of science like trapped ion research or Casimir effects arising at very close distances. Let me conclude this mechanics part with showing you one device that we're pursuing in our lab at the moment, where the idea is to take one of those large membranes and then implement a two-mode scheme where you have a non-local mode where the mode area 1 and mode area 2 are symmetrically or anti-symmetrically coupled. And then we can use a laser cavity on one end to do a very sensitive 10 femtometer readout, and the other end come in with a magnetic tip to probe samples located on the what we call a defect number 2. This was a cartoon. This is an experiment we're doing at the moment. And what I would say is one of the biggest advantages here that we can benefit from these years of experience in optomechanics, where many new resonator designs have emerged. And then combining with a large platform which is amenable to scanning on large area surfaces. With this, let me move on to optical and spin center nano MRI, and then finally conclude with STM. So if you look at the most prominent example here, it is the MV center in diamond. But to broaden this a bit, what you exploit in most of those techniques is that you have few but very well controllable electron spins. So you cannot detect the electrons one by one normally, or the nuclear spins, but there are a few select ones which you can probe using optical means and then use them as reporters or local probes for all the other spins surrounding them, being them electrons or nuclear spins. If you think of NMR signals, there are two geometries, big design principles you could think of. One is that you use single spins, truly single spins, and then you probe their local environment. But this again gives you very high resolution, but confines you to a very narrow field of view. So they're very short-sighted on this scale. Whereas you could imagine having dense ensembles shown on the right, where you have, in this example, a densely doped diamond surface, and then you would probe an extended sample area, but somehow you have to bring in the resolution in another means. For example, using a gradient coil, using an optical beam, but the resolution you may achieve is not really at the single-digit nanometer scale anymore. So let me, in the following, continue with the left picture, because this is really what brings us down to the low nanometer scale. So one of the big challenges that comes in there is, which a challenge that comes with most of those nanoscale probes, and this is famously quoted by this gentleman on the right, which gives the name to one of our main roads on our campus, Wolfgang Pauli, who once said that the bulk was made by God, but the surface was designed by the devil, and we really learn this every month in our lab. And if you think of these spin centers, there are many things that can happen if you have them close to surfaces, and you need them close to surfaces to probe NMR type of signals. In the case of the NV center, it has a negative charge state. This can change to neutral, and this may also happen to other types of defects because there are charge traps all around and mostly on surfaces. You could also imagine that the surface has many unwanted spins. So you may put a sample there, let's say it's a biological sample, but probably there is other stuff there, which is certainly not doing any good to your spin. And then even if diamond is a very rigid lattice, it has carbon-13 nuclei, it has other defect centers that have some background magnetic noise that perturbs your spin of interest. So you have to work in ways to try and reduce them, and actually you have to reduce them with any kind of near-field probe. Also, if you have mechanical sensors, if you have electrical noise, it creates similar issues. And finally, if you use several of those sensors, there will be inhomogeneities because you're working in a solid. So no device is exactly the same as the last one. No spin center is the same as the other. And if you measure several at once, then this creates some inhomogeneity effects. Also, if you have mechanical sensors, they're not always exactly the same, and they're better ones, they're worse ones, and you have to live with this. So somehow have to find a way around this, and I would say one of the big challenges moving forward is really just to learn how to control, prepare surfaces, which sometimes is trial and error, sometimes there's strategies, but it's one of the big issues at this low nanometer scale. Excluding STM, which is of course very well controlled, but for these more ambient type of techniques. Let me walk you through a few, which I think are very neat experiments showing the potential of this technique, but they're all done with NV centers deep in diamonds and surrounded by a dilute lattice of carbon-13 nuclear spins. So this could mimic a molecule which is built of individual carbon-13 atoms, but you have this as a testbed in diamond. The cartoon I'm showing here is from the Taminiau group in Delft, but the idea here is to take one NV center or defect spin and then have hyperfine interactions with all the nuclear spins, forming a cluster around it. And now you can start probing either the individual interactions between your electron and the nuclei, or if your spectral resolution in the NMR is high enough, you can probe the couplings along the nuclear spins and build up a nuclear spin network. So this second approach is essentially what's done in biological NMR. Many resonances are measured and the local couplings are established, and then with all these couplings available, you have a huge database where you can try and build a network and finally a spatial model from. Here's an example of the spectrum that you reach for this type of network. And this is a very amazing spectrum if you think of that this has been measured on with a single electron spin. You get similar maps routinely for biological NMR on zillions of spins, but not really for single spins. You can then use this, and in this case, to construct a 27 nuclear spin cluster. And this is all built upon that you can detect the nuclear spin-spin interactions and have this network available. In our lab, we have tried out a slightly different approach, which is in a sense complementary, is that you don't look at the couplings among nuclei, but you really, in a very sensitive way, analyze all the hyperfine interactions from your central electron spin to all the surrounding nuclear spins. So like doing astronomy, you're sitting at the Earth position and you look at the distances and spatial angles of all stars around you and try to find out where they're located. You can also build up maps with this, but they're of a different type in that you mostly are referenced to your central electron, so you get a broad picture, but you don't really get the local network character. So looking forward, one way could be to combine the two to really get a global view by measuring the couplings to a central electron and then build up a network in local pockets of your nuclear spin cluster. So with this, I would like to share 2 slides of ESR STM, which is not my primary technique, but I'm amazed by how well controlled they can do very high resolution experiments on surfaces. So just to introduce you to the principle here, most of you probably are familiar with STM. So you have a tip, you can bring it very close to the surface and then measure a current and regulate on this current, maybe also do spectroscopy by varying the voltage. So if you want to do this ESR STM, so spin resonance, you in addition have an antenna. So you have a high frequency microwave that if you tune it to the resonance of a spin, let's say one on the surface, this modulates the tunnel current, and then that way you can detect the electron spin. So this is quite different from what you've seen before, where we have a detector, let's say a mechanical detector, and we have a gradient given either by a small magnet or even by the defect spin itself. In that here, the measurement is done through a current, and it's a bit of a convoluted effect that you're both measuring a current and at the same time detecting the resonance from spins. However, you can still push this to great lengths in that you take one spin, which you use as your main probe, so very similar to the defect spin case, and you look at the interaction that spin has with other nearby atoms that you deterministically place. And these atoms may also have a nuclear spin, so it would allow you then in a chain fashion to also probe the nuclear resonance of those spins. So you see a few examples here. We'd have the purple spin on the left to probe the dipolar interaction to nearby other atoms with a magnetic moment. You can probe the hyperfine interaction of an electron with its intrinsic nuclear spin, or you can, on the right side, put two spins close to each other such that the interaction is not purely dipolar, but it allows you probing also other types of interactions like the exchange interaction. So it's a different test bed, mainly a way to probe interactions, maybe not to probe materials or biology at the big scale, but to have engineered systems to look at these interactions atom by atom. So with this, I think I'm at the end of my presentation, and I'm looking forward if there are any questions you have that you can ask through the chat.
Thank you very much for sharing this, Christian here. Please remember also to give questions in the chat here. So there's a question here. So you mentioned that atomic resolution could be achieved with nanomechanical oscillators. My understanding is that the distance of the tip to the sample typically limits resolutions. Could you explain how this works?
Yeah, good question. So the resolution in the mechanical case, where a magnetic tip or sometimes an electromagnet is involved, is mainly set by the gradients that we can achieve, because we need to spectrally distinguish spins. So this is an MRI principle. And also by the smallest volume spins that gives us a detectable signal. So now if you look at scaling behavior, the closer you get to your tip, or the smaller the distance between your sample and tip, the higher the gradient, which, let's say, for the mechanical means higher gradient gives you a higher sensitivity and also a higher imaging resolution. So naturally, if you make the distance smaller, because the gradient goes up, because your sensitivity goes up, you have a higher resolution. So this is where the distance comes in into the resolution.
Okay, thank you. Another question here. What do you think is the promise of spin centers beyond NV centers?
Other very good point. So you could ask yourself, why does everyone use NV centers? And okay, you'll get different answers. Mine is they're quite easy to learn if you're a beginner with a new lab. So it's a low entry barrier, and there's a lot of interesting experiments to be done. The second one, maybe more relevant for all this sensing, is it has a range of properties that make it very useful for these type of scanning experiments. You can put it in small tips, you can operate it at room temperature, it has a reasonable coherence, the optical readout works. And if you look for another spin center which fulfills the whole long list of properties that you need, so it's a logical and, to make your experiment work, it's very difficult to find one. There are many others, and they're intensively researched, and they outperform the NV on one or sometimes several properties. But for this type of exact sensing we're looking here, I wouldn't say there's another one which just clicks all the boxes on this long list of properties you need.
Okay, another question here. Can you describe the challenges of nano EPR compared to nano NMR?
So all these techniques have been applied to EPR and NMR. If you start to try these experiments, EPR is usually easier because the signals are larger. But if you think in terms of biology, molecular structures, NMR is by far more powerful than EPR. So I would say NMR in a sense is more challenging because signals are smaller, but the possibilities are much larger. However, both have their validity, and you can also come up with very exciting experiments and also routes for biology, for example, for EPR. Or if you think of defects in surfaces, moving away from biology, often these are paramagnetic defects, and then you would naturally study the EPR.
Yeah, maybe a last question here. Which strategies are used for controlling the diamond surfaces?
Okay, so for this you have to go deep into surface chemistry. I mean, the ultimate metric you have is you look at NV centers very close to the surface and analyze their properties. And then you start doing surface modifications, different preparations of diamonds. Most of the results are empirical in nature. So if I have to give you a number one recipe, you just need an as smooth and as clean diamond surface as possible. That is oxygen terminated. So this is the one known fact. If it's hydrogen terminated, it's unfavorable because of a band structure. But otherwise, I would say just well-controlled, clean diamond surface is what you need for best properties.
Yes, thank you. Thanks a lot here. In the interest of time, let's move on here. I'm going to invite Claire Dunphy to the stage here. Please also share your screen, Claire, when you're ready. Yes. I'll introduce you in the meanwhile here. So Claire Donnelly completed her PhD on X-ray magnetic tomography in 2017 at the Paul Scherrer Institute and ETH Zurich. After other positions at ETH Zurich, University of Cambridge, and the Cavendish Laboratory, she then moved to the Max Planck Institute for Chemical Physics of Solids in Dresden, where she has been a Lise Meitner group leader of Spin 3D since 2021. Here she has been studying physics of three-dimensional magnetic and superconducting systems and been developing synchrotron-based X-ray methods for resolving the structure in 3 dimensions. Thank you very much. You can take it from here.
Perfect. Thank you very much for the introduction. I hope you can all hear me okay. So I'd like to first of all thank you for the opportunity to speak to you a bit about our contribution to this really nice roadmap, which is something that I wrote together with Felix, Ofer, Wen, and Sergey. And the topic of our section is the question of coherent X-ray imaging and how this can be applied to magnetic systems. So what I'll try to explain in the next 20 minutes or so is a bit about what coherent X-ray imaging is, why this, so what are the advantages, how do we actually do this, and where might this be going in the next few years. Okay, but let's start off with a quick introduction into coherent X-ray imaging without the magnetism. And I think the point that I really want to make clear here is especially for synchrotron X-ray, the synchrotron X-ray community, coherent X-rays, in particular ptychography, have really revolutionized X-ray microscopy in general. So there was the first demonstration of ptychography in 2007 with X-rays, and since then really the high spatial resolution imaging in 2 dimensions and 3 dimensions has really blossomed. And it's only just this year, a few months ago, you see here this nice paper where yet another world record was met or broken for X-ray imaging, in this case using coherent X-ray imaging to do 3-dimensional imaging of an integrated circuit with 4 nanometer spatial resolution. So you can see that with these coherent imaging techniques, what people are really mostly thinking about is the fact that you really have the possibility to go beyond the limits of optics and really approach diffraction limited spatial resolutions. Now for magnetic materials, there has been also a lot of work done in trying to implement coherent imaging and their advantages for magnetic systems. And let's say the first couple of examples of magnetic coherent imaging were already in 2004 with the first demonstration of Fourier transform holography, and then more recently around just over 10 years ago where there was the first demonstration of magnetic ptychography. And these let's say words I will explain in a few more slides. Now, since the first demonstrations of coherent X-ray imaging for magnetism, there's really been a huge surge of works, both experimental developments and also scientific, let's say, insights resulting from these techniques. So for example, it's been possible to really push the dynamic imaging, tracking, for example, skyrmion dynamics, extending our 3D, our magnetic microscopy capabilities to 3 dimensions, and also by looking at using X-ray free electron lasers and also synchrotron radiation, really extending the capabilities of dynamic imaging for magnetic materials. Now, when we think about what coherent imaging is, we see, okay, I've shown you hopefully so far that there's a lot to be excited about, there's a lot going on. But I want to first of all take a quick second to think about what we actually mean by coherent imaging. And when we think about coherent imaging, especially for X-rays, we have 3 main, let's say, parts, so to speak, of the technique. We have to, of course, have a source of coherent light, which if we're looking for magnetic materials, we typically use circular polarized light. This light is then incident on our sample and typically goes in transmission, where we then record our coherent diffraction patterns in the far field. And these coherent diffraction patterns are almost like sort of interference patterns. They encode information about the sample interacting with the probe that's incident on the sample. Now, from these diffraction patterns, which is what we basically our raw data, we then use computer algorithms to reconstruct images, real space images of our magnetic materials and magnetic systems. And in principle, there's a couple of main techniques. So there's a number of different types of coherent imaging techniques, but the 2 main techniques that I'm going to speak about today, the first one is Fourier transform holography, and the second one is known as tychography. So what do we really mean by these 2 techniques? Well, first of all, I want to go into Fourier transform holography, which from a couple of slides ago, you might have seen or might remember that this was the first demonstration of coherent X-ray imaging. Now, the principle is actually relatively simple. We have, let's say, X-rays incident on a sample, and essentially what you have on the far field in the detector is the interference pattern between your object and a reference beam. And basically, when we have this interference pattern known as a hologram, which you record in the far fields, you can simply do a Fourier transform of this hologram and recover real space images of your magnetic configuration, which are essentially looking at the autocorrelation of the point reference beam and your object. Now, how is this actually achieved, this reference beam and this object? Well, for Fourier transform holography for X-rays, this typically involves these gold masks, which are about 1 micrometer or more of gold patterned. And you can see that an object hole, so to speak, is defined by etching with the focused ion beam, where you can see that the magnetic material, the magnetic thin film, is retained. However, then we also have next to the object hole a reference hole where the fib milling goes all the way through both the gold and the sample, and this provides this nice point reference, which can then interfere with the transmission function of your sample. Now, what's really nice about this holography is there's a couple of things. Now, no X-ray optics are involved, so you obtain this 15 to 20 nanometer spatial resolution without the use of optics. The resolution is actually defined more by this reference beam instead. And in principle, these are drift-free. So because the reference beam and your object are very well fixed with respect to one another, any instabilities in the sample do not actually impact the data at all, meaning that it's very robust. Now, secondly, the technique that I personally make more use of typically is X-ray tychography. Now, tychography is a slightly different version of coherent diffractive imaging in the sense that we don't have a reference beam, so we're not actually looking at the interference of a reference beam and the transmission function of our sample, but we're purely looking at the coherent diffraction of our sample, again in the far field. Now, in order to be able to recover the transmission function of our sample, we measure such, let's say, coherent diffraction patterns for many overlapping areas of the light on our sample, meaning that we have a set of, let's say, could be hundreds of diffraction patterns with a certain amount of redundance because you have a lot of this of the object positions overlapping with respect to the beam. We then use slightly more intense reconstruction algorithms, which are typically iterative reconstruction algorithms. But again, what is really nice is that you really are not limited by the lenses of your technique. So if we compare, for example, in this nice paper, scanning transmission X-ray microscopy, which involves scanning a nano probe across a beam, and what you would get from the same sample in tychography, you can see immediately that in tychography you have this beautiful high spatial resolution imaging with really high sensitivity, and you're essentially going beyond the limits of the optics. Now with this, hopefully you're getting a feeling for the fact that we have these relatively robust techniques that give us very high spatial resolution imaging. And what is really nice is that we can actually implement these with both synchrotron and lab-based sources. So with the synchrotron sources, many of you will be familiar with this. These are user facilities that pretty much everyone has access to, and they provide access to hard and soft X-rays. Lab-based sources are slightly more, let's say, need a certain amount of expertise, but it's possible also to have a source of EUV or soft X-rays in the lab. It's originating from a laser. And actually both of these sources provide coherent light, meaning that you can use them for coherent imaging. Now, because we have X-rays, what is really nice is that we combine this coherent imaging advantages with the advantages of X-rays for magnetism. And when we think about X-rays for magnetism, I would say the key advantages that we would like to highlight is the fact that we can be element specific, and also that we have sensitivity to the magnetization. Now, what do we mean by this? Well, when we think about the sensitivity to the magnetization, typically what we can do is we take our X-ray energy, we tune it to the resonance edge of a magnetic material, and we exploit X-ray magnetic circular dichroism. And essentially, if we have circularly polarized light, whether the beam is parallel or anti-parallel to the magnetization, you get huge differences in your refractive index of your material, meaning that you can actually isolate with the X-ray magnetic circular dichroism transmission projections of your magnetic configuration. Now, of course, I mentioned that this can be element sensitive, and this is exactly because of the fact that we are working at resonance. So every element will have different energies corresponding to its absorption edges, meaning that you can independently target different elements in your sample. And in this way, it's possible, for example, for magnetic materials to look at ferrimagnets, where you can look at the different sublattices, if these are different elements, for example, or even synthetic antiferromagnets, where you can again probe the different layers within your sample. So you see now we have, let's say, the possibility for coherent imaging, so the advantages of this, and the prospects or the power of X-ray spectroscopic techniques that we can combine together. And so when I'm mentioning these advantages of coherent diffractive imaging techniques, I want to sort of highlight in the next few slides three main aspects. The first one is this question of lensless imaging. I'll dig into a little bit more about why this is important. Secondly, I want to talk about the fact that with these reconstruction algorithms, we get the complex transmission function, so not only absorption, but also phase information. And lastly, I want to touch on the fact that these are very well suited for single shot measurements, which really lends itself to dynamic measurements. But let's start off with our lensless imaging. And the question maybe for you is, why do we care about lensless imaging? So if we think about the optical regime, typically, let's say, lenses are very well made and you can easily achieve diffraction limited imaging. However, in the X-ray regime, well, one advantage that we have is that X-rays are highly penetrating, so we can look in transmission through relatively thick samples. But this makes it actually very hard to make refractive optics. And so actually focusing X-rays down to the order of magnitude of their wavelengths, which can be nanometers or below, is incredibly hard. And actually what people turn to instead of refractive optics in X-rays in general are diffractive optics such as Fresnel zone plates. And these typically are designed by nanofabrication techniques, where actually the resolution or the size of the spot of your focused X-rays depends on how the resolution of your nanofabrication. So if you're aiming for 10, 20 nanometers or so, you can imagine creating these zones with high aspect ratio with a spacing on the order of 10 to 20 nanometers is really challenging. This essentially represents the limit of standard X-ray optical lens-based X-ray imaging techniques. Now, again, with coherent imaging, we can go beyond the limit of these optics to diffraction limited imaging, which really means ultimately wavelength limited spatial resolutions, maybe in the future. And there's already been some demonstrations of this for magnetic materials. So for example, going back to our holography, with adding in some additional more complicated reconstruction algorithms, It's been possible with soft X-rays to reach 5 nanometer spatial resolution, and even with this EUV light to go towards 16 nanometers. So you can see already that we can go far below what is typically achievable with scanning transmission X-ray microscopy or so, which is on the order to 20 to 30 nanometers. And it's even starting to approach, let's say, the spatial resolutions of electron-based techniques. Now, if we go to tychography, we also are looking at similar levels of spatial resolutions. So in 2 dimensions, we have this nice imaging of magnetotactic bacteria with 7 nanometer spatial resolution. And even in the last year, I think it was published last year, there's this very nice demonstration of going to 3-dimensional magnetic imaging with soft X-ray tychography, where we can really now aim to go below 10 nanometer spatial resolution. So this is really revolutionizing the kind of spatial resolutions that we can achieve experimentally for magnetic materials with X-rays. So we have our lensless imaging. Now, the second aspect that I want to talk about is this question of the complex transmission function. And in order to understand why this might be important, I want to think a little bit about the current limitations of, or one of the other current limitations of our standard imaging techniques with X-rays. So when we're thinking about transmission X-ray imaging or transmission magnetic imaging in general, we can think about what we might be looking at. We want to look at different types of materials. We want to be able to look at samples where we can give the materials enough space to form complex configurations. And we need, of course, our high spatial resolution. However, at the moment, we have a bit of a conundrum. So we always have to compromise. Of course, we can go to hard X-rays, so high energy X-rays, where we have plenty of space. But there we actually have very weak magnetic signals, meaning that we have, let's say, for a few materials such as the gadolinium, you can see here, very nice spatial resolution and very high sensitivity. But for iron, for example, as you see on the right-hand side, if you squint, you can see the same stripes. This is the same materials, iron, gadolinium multilayers. But basically, our signal to noise is absolutely awful due to the very, very weak signals at the transition metal K edges. Now, on the other hand, we have soft X-rays and electrons in transmission. We have much stronger signals, meaning we can look at a wide variety of materials. We have very high resolution, but we're typically limited to thin samples. And this actually is, so the question, of course, is can we combine all three? Can we actually achieve high spatial resolution imaging of any material we want in any sample geometry we want? And this is actually where coherent imaging has offered a solution. Now, in order to understand this, I just want to quickly touch on our standard type of magnetic imaging with X-rays, and this is absorption-based contrast. So here we have our transmission function, and we have our transmission spectrum, where you can see the absorption edges, where we have highest absorption, and the red line is our X and CD signal. And you can see for the transition metal L edges, this is very nicely centered on absorption, meaning that when you measure on resonance, your sample is effectively much thicker, and you can then therefore measure much thinner samples. However, when we look for where we use coherent diffractive imaging techniques, we actually have access not only to the absorption information, but we also recover the phase information. And now when we look at the spectroscopy of this, we can see in this blue line is our phase X and CD spectra, which rather than being only appearing on resonance, actually exists at almost all energies across the spectrum, specifically in this pre-edge area where we have much higher transmission. And so one of the questions that we were thinking about was, can we actually use this to combine our high X and CD signal with looking at thicker samples? And indeed, we were able to do this because, so we can think about looking at iron gadolinium multilayers as a first demonstration, going up to almost 2 micrometers in thickness, which is 1 order of magnitude thicker than would typically be measured with soft X-rays. And as we go up and up in thickness, we can see that with this phase contrast imaging, we're actually able to retain the high spatial resolution imaging up to almost 2 micrometers, meaning that we really now have this new capability to image magnetic materials with this coherent imaging techniques, with this phase contrast imaging. Okay, so lastly, so we've got, so far our lensless imaging, we can go towards diffraction limited spatial resolutions. We've got the complex transmission function, which gives us phase imaging, which allows us to look at much thicker samples. And now the last advantage I would want to highlight for coherent imaging is the prospect of single shot imaging. And what I mean by this, well, when we think about dynamic imaging in general, we typically have a compromise that needs to be made, right? So they see this, you will all be very familiar with this image here, or similar, let's see, images that you'll have seen in your life. The idea here is that we have the cars moving very fast. We don't have enough statistics in our image to be able to resolve them. So if we measure enough statistics in order to get nice statistics in the image, the cars are blurred out. And exactly the same principle actually applies for magnetic imaging as well. So when we think about taking a stack of images, let's say using our Fourier transform holography, if we were to measure long enough that we have nice statistics in the image, we see that the image is relatively blurred. So we have the black and the white regions, but we also have these gray regions where something's going on. But if we want to actually image fast enough to potentially identify, let's see, images where things are static, we have much weaker contrast, much lower statistics. Now for coherent imaging, we actually have an additional advantage, which is although for the real space image, you need many statistics to actually recover what's going on in the things. When we look at the coherent speckle pattern, which is this interference pattern in the far field, just a few photons can be enough to actually identify how the state has changed. Meaning that if we actually work in Fourier space rather than in real space, we can much more efficiently identify different configurations of our sample. And this is something that Felix and colleagues have actually been pioneering over the last few years. They've been working in Fourier space, doing some correlative, so cross-correlation between the different holograms in order to actually identify and cluster different magnetic states. And in this way, it's been possible to actually extend dynamic magnetic imaging to kind of a new direction. So you've typically always had quasi-static imaging, you've had resonant like pump probe, stroboscopic imaging, and here they're actually able to move this now to more fluctuating dynamics or incoherent magnetic imaging, which is a pretty exciting possible application of CDI. So what comes next? Okay, so in the last minute or so, I want to address some hopefully future things to look forward to, where we really see a lot of prospects for applications and advances. And again, we can come back to each of the different let's see, ingredients of CDI for this. So first of all, if we think about our source of coherent X-rays, we are very lucky because at the moment there's upgrades going on of third generation synchrotron sources around the world. And exactly what is going to benefit with these new sources is that the coherent light goes up by orders of magnitude in places, meaning that it's exactly these coherent imaging techniques that will benefit from these upgrades in sources, meaning that we will get essentially more statistics, higher resolution, faster measurements almost for free. Secondly, we can think about designing new types of techniques, new types of imaging. So for example, going towards different types of dynamic imaging, as Felix did in the last few slides, to higher dimensional imaging, which is something that I work on a lot. We can think about detectors. At the moment, the detectors, the dynamic range of the detector is really a limiting factor. There's a lot of work going on with colleagues in different places who are developing new detectors, which allows us to actually think about making the most of all of this coherent flux that we have. And lastly, it's about the computer algorithms. So as we know, with the huge, we have essentially a huge amount of data. We have this problem basically of big data, and we have a lot of work going on into not only developing algorithms to maybe target different types of physics, but also streamlining and potentially making use of AI and machine learning to actually be able to, again, make the most of the data that we have. So there's a huge amount of prospects for really advances and ways that we can improve, let's say, not only our data, but how we actually make the most of our data in the future. So I showed this at the first slide, and I want to finish with this slide basically. So we have quite a lot. It's very nice to actually think about how things have come over the last few years. We've really seen a bit of a surge in interest and actually the use of coherent imaging for magnetic systems. And I think in the next few years, what we're really looking forward to is making use of these new synchrotron sources, going towards more operando techniques, looking at different sample environments, and hopefully convincing more and more people to make use of CDI for their own measurements. But thank you very much for that, and I'd be more than happy to answer any questions.
Thank you very much, Claire. I think we have a couple of questions here. So one of them is, can paramagnetism be detected in these measurements?
Paramagnetism?
Yes.
Oh, so okay, so I think I had put this on one of my slides. I would say at the moment, this is a matter of sensitivity, right? So in principle, it should be, but I would say at the moment we are more limited by limited at the moment to ferromagnetic and antiferromagnetic samples, purely due to the strength of the signal. I'd say in the future, I would not rule out. I think there's nothing really stopping us from actually measuring the paramagnetic state. But let's see, this is not something for today, but potentially something to look forward to in the future. Yeah.
Thank you. Another question here. Do these measurements require a beamline or special source? And what are the prospects of developing tabletop setups?
Yep, so this is something that I mentioned very quickly, but I can go into more detail. So yes, the vast majority of work on coherent imaging is actually taking place at synchrotron beamlines. So this is these are user facilities typically. These are something that everybody can apply to, and let's say it's very much the case that in the last few years there's been a growing number of beamlines that will actually offer coherent imaging for magnetic samples. Let's say probably 5 years ago it might have been 1 or 2, and now we can really see this starting to take off. So it's really the start of this technique. And I would really recommend, if people are interested in this, I mean, they can get in touch or have a look at the beamlines. Now we have beamlines in the US, across Europe, and also in Asia, where this can really be, where you can really go and take your samples and do your own measurements. For the tabletop techniques, this is something that's been really pioneered by Ofer and Sergey and colleagues who were the co-authors of the section of the roadmap. Basically, the idea is that they make use of higher harmonic generation from laser sources, and with this, in this way, you're able to create coherent sources of very low energy X-rays, or this EUV, extreme ultraviolet radiation. Now, what's nice is actually you can still reach a few absorption edges with that, so you can still apply the same principles, and again retaining the ultra high spatial resolution. So you have longer wavelength X-rays, but still the wavelengths are on the order of tens of nanometers, meaning that with this diffraction limited capabilities, you can still really in the lab get spatial resolutions on the order of 10 or 20 nanometers, which is really, I would say, pretty cool. Yeah.
Yes, thank you. Maybe we have time for one more question here. So are coherent X-ray techniques sensitive to currents or only magnetization?
Aha, this is a very good question. So in the end, I think in the end is the answer, I guess, would be no. So not in the way that, for example, the scanning squid or the scanning NV might be. So as far as I understand, with those techniques, what you're measuring is the Ørsted field of the current, right? And what we are doing here, what's slightly different, is that we're really directly probing the transition, the atomic transition. So we're really probing the magnetization of our sample. So what that means is that we're not sensitive to the motion of electrons, but you're sensitive, for example, to electron density or local, let's say, imbalances of spin up and spin down. And what is quite nice actually is there's been a paper I think it was last year or the year before, where there was the demonstration of X-ray imaging of the spin Hall effect, so the spin Hall accumulation. So even though you might not be able to image the currents directly, you can image current-induced effects and spintronic effects quite nicely as well, and quantitatively, so you can really disentangle spin and orbital moments and so on. So there's a lot of prospects there, and it can be very complementary, I would say, to the other techniques that have been presented.
Yes, very exciting. Maybe one last one here. Why use harmonic lasers as source?
Why use harmonic lasers as source?
Yeah.
Okay, good. So what I was meaning, I think this is referring to the higher harmonic generation. Now, this is something I have to say I am not an expert in, so I would very much, let's say, refer to my colleagues Ofer Kfir and Sergei Zaiko. But the idea is not, so the idea is basically that you can use, let's see if I remember, you can use like laser sources and you pass them through a certain gas environment, and you can actually achieve higher harmonic generation, so the generation of higher harmonics. And basically, therefore, you increase the energy to, let's say, the EUV or the soft X-ray regime. So the reason why you would want to do this, of course, you could also do, for example, coherent imaging with just your laser. The reason that you would want to do this is to get smaller wavelengths, so you can get higher resolution. And then also that you can potentially target some of these resonances, so the absorption edges, to get circular dichroism or linear dichroism. But yeah, but for more details, I would say I'm not the expert here.
Thank you a lot, Claire. Let's move on then to Matthias Chloe. Please share your screen also. So Matthias Chloe is Professor of Physics at Johannes Gutenberg University Mainz and adjunct professor at Norwegian University of Science and Technology. He received his PhD at University of Cambridge, after which he joined the IBM research labs in Zurich. He was a junior group leader at the University of Constance and then became associate professor in a joint appointment between EPFL and the PSI in Switzerland, before he then moved to Mainz. Thank you. And I think you are muted here.
Now it's better. Okay, yes.
Perfect, yeah.
I was muted by the organizers. All right, good. Just quick check. Can you see my screen now?
Yes, it all worked out.
Okay. Perfect, great. Well, firstly, I'd like to thank, of course, the people of IOP as well as Christian for putting together this exciting roadmap. And I'm very happy that I'm the last speaker, so Claire has already convinced you, hopefully, that high-resolution magnetic imaging is something that is really, really useful. So I'm quite complimentary in my presentation to what you've seen by Claire, in that I will actually introduce to you a technique which is a purely lab-based technique, so no need to go to synchrotron, but it also has some advantages and some disadvantages compared to the imaging techniques that Claire introduced. So I will introduce scanning electron microscopy with polarization analysis as a surface-sensitive high-resolution dynamic magnetic imaging tool. So I'd like to acknowledge Robert Fremter. He's been one of the pioneers of developing this technique further, and he's also provided valuable input for the slides. So quickly, I'll introduce scanning electron microscopy-based magnetic imaging, including SAMPA. Then I'll show you how we can detect spin-polarized electrons, how to prepare samples for SAMPA, and also some dynamic SAMPA. So let's start. Scanning electron microscopy, you probably are mostly familiar with that. So you have an electron source, and then you accelerate the electrons to a couple of kiloelectron volts, and you focus them onto a sample specimen. And then you have backscattered electrons as well as secondary electrons generated, which are then detected by a detector. And what you typically do in SEM to image topographies, you simply have a look at the number of electrons that are detected, and you plot that as a function of the position of the scanned beam. Now, if you look at the secondaries, the electrons that you detect, depending on the energy, you have a large number of secondary electrons which have very low energy, and then you have these backscattered electrons where you have the Auger electrons, and you have also elastically reflected electrons. Now what you see is you have an electron beam, and these days you can actually focus your electron beam down to sub-nanometer sizes, depending on if you have a good aberration correction. And then you generate at the very top of the electron incident, you actually generate Auger electrons, and then further down here you have backscattered electrons, and actually the size of this electron interaction volume gives you also some information about the spatial resolution that you can get. So initially, there were a very simple way to actually have a magnetic contrast in a scanning electron microscope, and that was to use the stray field of the magnetic pattern to actually deflect electrons, and then this could be used to make images of the magnetic configuration. However, the problem is that the stray fields lead to a very poor spatial resolution. It's of the order of micrometer, but the advantage is you can do that with any scanning electron microscope, because you still collect simply the total number of electrons, which are then arriving at the secondary electron detector. So this is a technique which has been around for a long time, but it's not used much these days because the spatial resolution is essentially given by the resolution that is similar to the vertical extent of the stray field, which is of the order of a micrometer. Now, more interesting for us is the fact that the secondary electrons, when they're emitted, they actually have a spin polarization. So the polarization of the electrons, as you can see here, is a function of kinetic energy, is actually low for high energy electrons, but low, it's low for high energy electrons, but high for low energy electrons. You can get a polarization, for instance, for iron up to 50% for the lowest electron energies of the secondaries that you can collect. So above 20 eV secondaries, they typically have the D-band polarization of 25%, but at very low energies, you actually get internal spin filtering by trapping in minority D holes, and you can get up to 50% spin polarization from these electrons here. And this was shown first by Jürgen Kirschner and Koike and others in this, as well as Gerd Schönhense and Hans-Christian Siegmann in this paper here. So now what you need to do when you have these secondaries, which now reflect the magnetization of the material from which they were emitted, you need to, of course, detect them. And how do we measure the spin of these free electrons, these secondaries that come out? Well, you might think we do the Stern-Gerlach experiment, but that doesn't work because you, of course, have the electron charge, so Lorentz force effects will be much too large. So Stern-Gerlach only works for neutral atoms. So what you can do instead is you can use the spin-orbit coupling that is leading to spin-dependent scattering in a heavy metal. So, these days we use the spin-Hall effect, where you actually have the generation of a transverse spin current from a longitudinal charge current, and even in a non-magnetic material. But what is used for the detection of the spin polarization of the secondary electrons is, for instance, a Mott detector. So in a Mott detector, you have your electrons, your secondaries, you accelerate them up to 100 keV, and then, for instance, they are scattered from gold, which is a heavy material with large spin-orbit coupling, and then you have Mott skew scattering leading to spin up electrons scattered to the left and spin down electrons scattered to the right, and by simply counting the number of spin right minus spin left, you can get the spin polarization of the primary electron beam. Now this works very nicely. The efficiency is not amazing, but it's a relatively simple technique because you just need to accelerate your electrons and you hit a gold foil, and then you measure the number of electrons scattered to the right and scattered to the left. And you can see that here, this sensitivity is called the Sherman function, and then we can obtain this intensity asymmetry, which then is a measure of the spin polarization, which is essentially the Sherman function times the spin polarization gives our intensity asymmetry. And if you know the Sherman function, which is just depending on, for instance, whether this is gold or thorium or something like that, then you can determine the absolute polarization of the secondary electrons. So there's another technique. So this technique works very well, but you need to accelerate the electrons to 30 keV or higher. So when I was a postdoc at IBM, we had a 100 keV detector, and 100 keV is already a little bit dangerous. So there's another type of detector to detect the spin polarization of the electrons, which is a so-called split detector, spin polarized low electron energy diffraction detector. So here we find that actually there's a spin-dependent lead scattering, for instance, from tungsten 100 at a certain energy. So for a certain energy, so a relatively precise energy of 104.5 electron volts, you actually get an asymmetry of the intensity of these lead patterns depending on the polarization. And again, this asymmetry is now depending on this. And so you can actually get a relatively good sensitivity. And this is small acceleration voltage, just 100 volts, so it's not dangerous, but it's extremely sensitive to the quality of the surface of this tungsten 100 crystal. So you need to keep this tungsten 100 crystal very clean, and that means you need very good UHV. So in our system, we have a base pressure of low 10 to minus 11, and even that we do have to flash the crystal, a couple of times a week in order to have a very nice surface of the tungsten 100 crystal. All right, so now we can detect the polarization of our emitted secondary electrons, and this is then what such a detector really looks like. So this is the split detector, which here the secondary electrons are collected, and then they go through this transfer optics, which you see here, and then here's the tungsten 100 crystal, and then here you have channel plates, which are used to detect the electrons as they arrive here and here, and then again you look at the difference of electron numbers here and here. All right, and then here you see the convolution with the secondary electron energy distribution, and then from that you can deduce the spin polarization. So for the spin detectors for free electrons, we have the spin orbit coupling based spin detectors that I just described. However, the figure of merit typically is relatively low. It's of the order of 10 to minus 4. And that means you might have to take quite long measurements. So a single image, in contrast to what was shown by Claire, we actually need for a single image typically like minutes. And if you make a movie where you take many, many images in a pump probe scheme, it might be really many hours. So you might be 20 hours, which you take one movie. That has recently improved. There are new developments such as the ferrum spin detector, which is based on exchange coupling, which can have an order of magnitude improved figure of merit. There's also the split using gold iridium, which is also more sensitive, but one also has to be careful about the keeping the surface clean. So a priori, there are many ways to improve the detection, but that's one of the problems with SEMPA is that fundamentally the detection efficiency is relatively low, meaning that you have to have long exposure times. But since it's a lab-based technique, sometimes you simply don't care. You launch a measurement and you come back the next morning and you get a beautiful movie. So fundamentally, what we do is in order to use this to do magnetic imaging, we scan our primary electron beam across our sample. So here we have, for instance, a square in the Landau pattern where the magnetization rotates in this kind of vortex or 4-quadrant state. And then as we raster our primary electron beam across these different domains, the secondary electrons that are emitted essentially mirror the direction of the magnetization. So if the magnetization here is pointing to the left, most of the secondaries that are emitted have their spin to the right, since the spin is anti-parallel to the magnetization by definition. So if I now then scan across to this domain here, then now the secondaries will mostly have their spins pointing to the left. So then we plot the asymmetry as a function of the position, and then we can get the surface magnetization imaged. Now, there are many SEMPA realizations. I'd just like to point out some of the early ones that were published. So here from our Japanese colleagues, Koike et al., then John Ungeris at NIST is 1985, Hans-Peter Oepen at the time, I think, in Halle, then he was later in Hamburg, Rolf Allensbach, where I did my postdoc at IBM Zurich. So they're essentially all relying on the SCM column, which provides the primary beam, and then the secondaries, which are collected by the spin detector. Now, in order to have detection of different components, so magnetization components, you need to tilt your sample or you need to rotate the detector, but then you can get the full 3D information on the magnetization direction. So that's what it really looks like. So here you have your sample, you have got the SEM column, and then here you got the spin detector. You have a rotation in order to rotate the spin detector to obtain different components of the magnetization. Something that one should note is because of the sensitivity of the spin detector, at least the split detector, you need really good UHV, which means you cannot just add this as to a standard SEM, which is operating at a pressure of 10 to minus 6, 10 to minus 7. Here we really want to have a pressure of 10 to minus 10, 10 to minus 11. And so typically you have to put your SEM column onto a UHV chamber rather than adding the spin detector to a normal SEM. So then what do the images look like? So here are 4 images from our 2.0 lead beams. Then you see already there's some contrast, but now what you can do is you can make the sum. The sum just gives you the topography. And now we can do the asymmetry. And then we see here very nicely black and white for this component, meaning that here the magnetization is pointing down, here it's pointing up. And if we look at the other component, we see here it's pointing right, here it's pointing left. So overall, we have the vortex where the magnetization rotates clockwise in this spin structure. Then we can actually make a false color picture by combining these two. And then you see very nicely, yellow means magnetization up, red means magnetization right, purple means magnetization down, and green means magnetization left. So this is permalloy on diamond. And now one of the things that is very important is that this technique is extremely surface sensitive. This is good and bad. It is good because we can actually image very easily monolayers. There's absolutely no problem in detecting monolayers because it is so surface sensitive. The secondaries are emitted really from the top nanometer or so. The disadvantage is that if you have already 2 nanometers of dirt on top of your sample, you're not going to see anything anymore because the secondaries are then emitted from the dirt, which is obviously non-magnetic. So here, for instance, we had a bulk nickel 111 crystal and we put a monolayer of graphene and we prepared that in UHV and transferred it at air. And it turns out that graphene is very nice because graphene actually protects the surface against oxidation. So we really see already contrast across the one monolayer of graphene. Graphene is sufficiently thin so we can look through it, and then we can see the contrast. Now what we can then do, we can remove the graphene by a little bit of argon ion milling, and then the contrast improves from 1% to 3%. And then what you can do is a little trick. So we have nickel 111 crystal, and now to improve the contrast, we're going to put a material on top which has a larger spin polarization. Well, we're going to put such a thin layer of that material that the material itself does not influence the domain structure of the nickel, but just acts as a contrast enhancing agent. So in this case, it's 4 monolayers of cobalt, you get a contrast of about 5.5%. But if you put 4 monolayers of iron, you get a very nice contrast of nearly 10%. So this is kind of a way to enhance the contrast by putting such a very, very thin dusting layer, which does not influence the domain structure of the nickel because it's a bulk crystal, but at the same time, it enhances the contrast. Right, so here's just an example of what has been looked at in the group of Hans-Peter Oepen. So they looked at the temperature-driven spin orientation in neodymium cobalt 5. So at low temperature, you see here the magnetization is primarily due to uniaxial anisotropy pointing to the left and to the right. So this is like a 10 by 10 micrometer picture. And you see here, if you do a histogram, you see that most of the magnetization is pointing left or right, or virtually the magnetization is uniformly pointing left or right. Is a uniaxial anisotropy. But now as we increase the temperature, there's a reorientation of the anisotropy, and the twofold anisotropy at the low temperature phase is along the A-axis and the high temperature phase is along the C-axis. So as we increase the temperature, we see that there are now more domains appearing. Until about 285 Kelvin, you actually have a similar amount of magnetization pointing right, left, as up, down. So you get these 4 spots here, which indicate that you have roughly a cubic anisotropy. And then if you go to 320 Kelvin, you see that now all the domains are pointing the magnetization with the magnetization up or down along the C-axis. And again, in the histogram, you see now this vertical orientation. So now you can very easily understand how, as a function of temperature, the reorientation of the spins from along the C-axis, along the A-axis at low temperature to along the C-axis at high temperature occurs. And in the SEMPA, we can cool down to some 10 Kelvin and we can heat up to some 500 Kelvin. So that's also an advantage because it's in UHV. This is relatively easy to do. Now, one example, skyrmions are all the rage, and Claire actually showed very nice the dynamics of skyrmions that we published a couple of years ago. But you can also do imaging of the and at that time we only saw the skyrmion center. We could not resolve the domain walls. So here we are able to resolve the domain walls. So you see here that we actually have a nail domain walls with a fixed chirality, so going from up to down. You see we always rotate clockwise, and this is due to the so-called antisymmetric Dzierżynski-Moria interaction, which is due to the coupling of cobalt on the heavy metal iridium-111 surface. So this is a very nice tool because it's very high spatial resolution. It allows us to deduce the chirality of the domain walls, which for many other techniques, such as the imaging that I showed, that Claire showed you, we could not do. And we can even, from the width of the domain wall, we can deduce the absolute number of the Dzierżynski-Moria interaction. Now, if you want to image the full 3D magnetization configuration, then you need to either rotate the sample, but if you rotate the sample, then when you, for instance, go to very close to a grazing incidence, you actually lose spatial resolution. So what you can do is you can use a cylindrical mirror analyzer that is essentially bending the trajectory of the electron beam by 90 degrees while keeping the spin orientation of the spins fixed. So you see here, you emit electrons which have a spin to the right, and then you actually have, with the CMA, you bend the beam. So now the electrons are not anymore in plane as here, but they're kind of perpendicular to the flight direction, and then they can be easily detected by the channeltron, or vice versa. Here we emit from the SEM column, and then they have the in-plane orientation, which is then good for the tungsten 0001 split detector. Okay, so just to show you the sensitivity of the SEMPA to the surface, we see here that when we do a wedge of cobalt, that for low thicknesses of the cobalt, we have perpendicular anisotropy. You see here the out of plane magnetization, and as we increase the cobalt thickness, and you really start here at 1 nanometer cobalt, which is easy. You see very nice contrast with just 1 nanometer of cobalt, but then we get to actually for thicker, 2 or so nanometer of cobalt, we actually get very nice in-plane contrast. So the spin orientation can really be imaged with very high precision if we have some states which have both in-plane and out-of-plane component. Now we can image through a very thin platinum cap. But typically what we do is we actually sputter clean the surface of the sample, or we desorb the cap in order to get the best contrast. And we did some analysis, and we see here that here we still have a quarter of the contrast from the cobalt when looking through 1.1 nanometer of platinum. So that's actually pretty good, because 1.1 nanometer of platinum is typically sufficient to prevent also ex situ grown samples from oxidizing when they're put into the sampler machine. So it's not a technique that's only good for in situ, but it's also good for ex situ prepared samples. So just to give you a little bit about the resolution. So here, this is the best resolution that has been reported by Koike et al. So this is a resolution of 2.7 nanometer, but that's really pushing it. I mean, it's relatively easy to get like 10, 15 nanometers, but if you really want to push it, you can go below 3 nanometers. So this is really ultra high spatial resolution. Now, finally, just a few words about time-resolved SEMPA. So everything I've shown you so far, it was static. And of course, since we have this rather long exposure times necessary to get the contrast, we cannot do single shot, but what we can do is pump probe. So we can have a periodic excitation of our system, and then we can, by pump probe imaging, make a movie out of it. And in order to do that, what we need to do is we need to actually detect not just the number of electrons in the asymmetry, but also their arrival time. So every electron gets a timestamp when it has arrived. And then we can group the counts into time slices according to the phase of the driving signal to make a movie. So we get a vector movie for a periodically driven magnetic system with typically like, a nanosecond time resolution, which already provides quite a lot of information on, say, micromagnetic dynamics, which is governed by the LLG equation. So here is what it really looks like. at least schematically. We have your electron beam, which is a continuous electron beam. So we're not bunching the excitation by the electrons, or not bunching the electron beam, but we are reading out the electrons with the TDC, so time to digital converter, where every electron that's detected gets a timestamp when it arrived, and then this is analyzed and later bunched and then made into a movie. So here we have our example. So this is a strip line, where the strip line has a current that's injected to generate an Ørsted field. And typically this is, in this case, a gold microstrip line. And then we have a magnetic disk, and this magnetic or square, in this case it's iron nickel so cobalt, iron, silicon, boron, and it's an amorphous square. And now we excite the dynamics of the square by the Ørsted field from our strip line. And initially, this is such a 4-quadrant state, and then we inject current, which generates this Ørsted field, and that actually displaces these domain walls and the vortex core. And this is what it looks like statically initially, but then this is the dynamic movie, and you can see here how very nicely the Ørsted field displaces this vortex core here and also the domain walls, and you can actually see such a nice movie. So it took about 5 hours to make the movie, and the excitation is about 100 megahertz, so it's a 10 nanosecond movie, and the time resolution that we get is typically like 600 picoseconds to a nanosecond. All right, I just wanted to show you that we can also use the motion blur to measure the time resolution, so we can just see here how the whole image due to the Ørsted field shifts. We need then later to adjust that, but that actually allows us to deduce the time resolution. In this case, it's about 720 picoseconds, so a little bit sub-nanosecond. All right, my time is up. So I'd just like to thank all the people that did the work. So in particular, Robert Fremter, he's been really one of the pioneers of the Semper technique, first in the group of Hans-Peter Oepen, later myself. And these are all the people in my group doing with the work, in particular also Gerd Jakob and Martin Jordan, which are permanent staff scientists, as well as Peter Werner on the theory side. We had a lot of collaborations on this, and also we need funding. But I want to wrap up with the summary of how we can use Semper for magnetic imaging. And just to summarize, we have the UHV SEM column, which provides the primary beam. We have then the secondaries, and we essentially measure the polarization of the secondaries by the speed of the gold mod detector. If you look in here, you see that the secondary electrons, they mirror the magnetization of our sample, whereas the primary beam is unpolarized. And so the measured spin polarization of the secondaries is proportional to the surface magnetization. It's very high surface sensitivity of a nanometer or so. The speed detector works by having an asymmetry of the intensity of the lead spots due to spin-orbit coupling for a certain energy. And if you use Moss-skew scattering, then you just have to accelerate the electrons to very high voltages. You can get relatively high spectral resolution. As I said, it's been demonstrated better than 3 nanometers. 10, 15 nanometers is pretty standard. You can get a very nice high time resolution, 700 picoseconds, which for many of the dynamics of spin structures such as skirmins and so on is sufficient. It's very surface sensitive. As I said, we can have a monolayer that is easy to detect. It requires UHV because it is so surface sensitive. So if you have just a couple of nanometers of dirt on top, you're not going to see anything. It allows for 2D and meanwhile also 3D vector imaging. And I just would like to point you to these references here if you're interested in more details. And of course, I'm also happy to hear about your questions. And with that, I thank you for your attention, and I'm looking forward to the questions.
Thank you very much, Matthias. There. We have a couple of questions here. So one question is, can you play with the energy of the electrons to get additional information?
Absolutely. So maybe, am I still sharing my screen?
No.
Then let me just quickly share my screen again. Start screen sharing. Okay, does it work now?
Yeah.
Okay, perfect. So as I showed earlier, the secondary electrons, they have different information and different polarization depending on the energy. And you see here that you can actually learn something about the spin split density of states by choosing different secondary electrons. Typically, you don't have a huge amount of secondary electrons, so you need to bunch it a little bit. But by selecting like 5 eV or something, a window of that, you can actually learn something about the spin split density of states. So yes, absolutely.
Okay. Another question here is you're using cobalt and iron dusting layers to enhance the contrast.
Yes.
How do you choose the dusting layer?
Yes. Iron is typically the dusting layer which has the highest spin polarization. So of the 3D metals, iron has the largest spin polarization, nickel is the worst. So we choose typically iron. The disadvantage of iron is it's also the most prone to oxidation, so it has the shortest lifetime. So if you want to just have a nice quick image and you don't care much about lifetime of your sample, then this is best. The other thing that you have to take into account, that you have to be careful that your dusting layer does not influence the magnetic configuration that you'd like to measure. So it should also be a relatively soft magnetic material. So that's kind of the considerations you have to take into account when you do the choice of the dusting layers. Typically, iron is best because iron generates the largest spin polarization.
Yes. Speaking of also soft magnetic materials, another question here. Can you use an ultra-thin magnetic layer to detect current distributions?
Yes, absolutely, you can do that. But I'm not sure if this, it's something that can be done. I mean, you see here that essentially here we have a uniform current distribution and it excites the magnetization. So if you have like a device geometry where you don't know how the current flows, then you can actually do that. But there are other ways to do that which might be more efficient. For instance, you look at the deflection of the secondary electrons. You don't even need a magnetic material on top, but just looking at the deflection of the slow, low energy secondaries allows you to actually see the local Ørsted field and by that the current distribution.
Okay. Maybe a last one here. What is the detecting limit of the technique? How magnetic should the surface be to detect it?
Yes, so essentially what we're detecting is not the saturation magnetization, but what we're detecting is the spin polarization of the secondary emitted electrons. So one has to be a little bit careful that this secondary spin polarization is a complex function of the spin split density of states. So therefore one needs to think about the material that one looks at, that it has a large polarization of the secondaries. And that, there are some materials which have a large saturation magnetization but don't make very good contrast. And then there are other materials like LSMO, which is a half metal, highly spin polarized, has very nice contrast, but has a relatively low saturation magnetization. Also, for instance, if one looks at a ferromagnet like gadolinium iron or gadolinium cobalt or terbium cobalt, the secondaries are typically virtually exclusively from the transition metal. So if I have gadolinium iron and the gadolinium and the iron is anti-parallel, you have no net moment, but still the image that you get is very nice because they all come from the cobalt or from the iron, and from the gadolinium because you have the magnetic moments are deep in the shell. You don't get any significant emission of secondaries that are spin polarized. So you can even image the magnetization configuration of a ferromagnet at the compensation point where it has zero net magnetization. So that's a complex answer, but look at literature. People have looked at many, many different materials and found which ones are easy to measure and which ones are a bit more challenging.
Yes. Maybe time for a very last question here. Have you tried imaging the effect of spin transfer torques and spin orbit torques using this technique?
Oh, absolutely. So if you send me an email, so I didn't put my email address, but my name is pretty unique, so I'm very easy to Google. Send me an email. I'm happy to provide some of the references where we looked at spin orbit torque switching of devices, germion dynamics, all these type of things, using this technique.
Thank you very much, Matthias here. I think with this, I would like to conclude the webinar here. So thank you for IOP for hosting this webinar. Thank you for the 4 speakers. Thank you also to the audience here. So I'm concluding, ending the webinar here.
Thank you very much. Bye-bye.
Bye-bye.